hope I don't offend anyone by overlooking your recent work. But I do remember where some bodies are buried, and I know that there's some people in this specialist audience who might be interested in seeing all things that we didn't actually do right. And so I've sort of put this talk together in that spirit. And I'm also really excited to be here and talk to all of you who must be getting to be very, very well educated about this topic after 10 days of Newton workshops and so on and so forth. So that's what happens. So when you think you're talking to a specialist audience, you prepare too much material and then you bore everyone. So let's start with this. This is sort of phase diagram for geophysicists. So we're looking at a bunch of experiments on partial melting of mantle peridotite as a function of the pressure of melting and the silica content. And basically up here we have andesites that are in equilibrium with mantle peridotite at low pressures, and picritic basalts in equilibrium with peridotite at higher pressures. And in order to follow this trajectory, melts ascending through the mantle have to dissolve the silica-rich phases, the pyroxenes, and precipitate olivine. And we can look at that dissolution reaction and the enthalpies and entropies involved and see that the dissolution reaction, where we have a liquid that's rising through the mantle, it's going to dissolve pyroxenes and make a new liquid which has more silica in it, and it precipitates an olivine. And we can see that that reaction will increase the liquid mass. So the amount that's dissolved is larger than the amount that's precipitated, and this can make increasing porosity, which interacts in an interesting way with viscous compaction. And we'll use phase diagrams and math, or whatever your favorite way, to look at the solubility of orthopyroxene in melts about 1% per kilobar. So as melt ascends through the mantle, it's going to dissolve pyroxenes that it encounters. The other very basic thing is to think about permeability in the mantle. This is actually a picture of reticulate, so a silica glass foam from lava in Hawaii. But it's thought to be a close approximation to the triple grain boundary network that forms around olivine grains in the mantle. So you can sort of mentally replace the air in this figure with olivine crystals, and you can see these triple grain boundaries along the grain triple junctions. So one of your favorite sons, Mark Spiegelman and Pam Kenyon, many years ago developed some scaling relationships that are useful for thinking about upwelling of the decompression melting of the mantle beneath mid-ocean ridges. And they came up with the approximation that, for example, the porosity at any given height in this decompressing column that's undergoing partial melting is roughly equal to the upwelling velocity, big W, times the melt fraction at that height, F, and some densities to scale things, divided by the liquid upwelling velocity. And I've put this chi in here. Later on we'll make that chi some value less than 1, and it's going to represent the volume fraction in the mantle in which the melt is actually moving, so channels or no channels, but for now we'll make chi 1, there's no channels. So they have this one-dimensional steady state way that if you know the porosity and the upwelling rate and the melt fraction, you can predict the melt velocity and so on. And then we also can imagine that there's something like Darcy flow of melt in those triple grain pores. And then we're going to relate the melt velocity to some permeability, the difference in density between the melt and the solid G, and the viscosity, the porosity and the viscosity of the melt. And so there's been some argumentation about how that permeability law ought to look. And so going back to von Bargen and Waff in 1986, if it's a perfect triple grain boundary network of the type that I showed you, you can use geometry to predict how the permeability will vary with the fluid fraction. And the von Bargen and Waff prediction in this is this gray line in this diagram, and probably the numerical line in this diagram. And on the other hand, Uli Fowl has been very influential in doing experiments and showing that sometimes melt is not only on those triple grain boundaries, but also on grain-grain faces. and he proposed that this might have some effect on the permeability. And initially he proposed it would have a rather large effect on the permeability, and so he has this very different kind of permeability law with a permeability threshold at about 2.5% melt. And that would make a big difference for all kinds of things we're going to look at in the course of this lecture. So it was important to figure out if he was right or not. And I think I eliminated a bunch of slides of other people's work on this, but suffice it to say that people like Bruce Watson and Dave Wark and Yan Liang and so on worked on experimental samples, particularly quartzites with water in them, in this red line, and various other things, and tried to empirically look at the melt geometry and the permeability in various analog and olivine melt systems. But Dan McKenzie was always after me to try and do this with natural samples, and his argument was that we were overlooking trapped melt. That we were looking at these dunites, for example, that I'm going to talk about, so olivine-only rocks with a little bit of chromium spinel. And I would say, Dan, there's no melt in these rocks. So the permeability had to be pretty high in order to extract all that liquid before they became completely solidified. And he said, well, you know, you're not really looking hard enough at the grain boundaries, and you know there's alteration phases on those grain boundaries, so maybe there was a liquid fraction of 10 to the minus 3 or something like that trapped in those rocks before they solidified. And so we finally got it together to take a look at that. And we're using various kinds of chemical variables. Calcium is one that's pretty much excluded from olivine and the other mineral constituent spinel in these rocks. But it might remain and crystallize trap melt on the grain boundaries. And we also use aluminum and various other things. And we can put bounds on, we can analyze the olivine and the spinel in the whole rock and see how much calcium is in the whole rock that we can't account for by the calcium in the minerals, and get some idea what sort of microscopic or submicroscopic trap melt fraction might remain in these dunites. And you see that it could be 0. You can get some negative values, but they're uncertain. And so it should lie somewhere between, let's say, 2% and 0.2% and maybe 0.5% as a maximum. The first thing we can say is that the empirically derived from natural rocks, the empirically derived permeabilities have to be greater than 10 to the minus 17 or 10 to the minus 16 meters squared at these low porosities, and therefore this idea that wetted grain faces make a big difference to the permeability is not correct. They might be wetted grain faces, they might matter a lot for attenuation and rheology, but they're not making most of the melt is in these almost tubular pores, so it doesn't really matter.
And that's making an assumption about the geometry of the pores, that they're always connected?
Well, of course, that happens to be consistent with what I just told you based on rocks. But yeah.
It also comes into the definition of fine. The porosity, the connected porosity.
True. But again, these are the kinds of reasons why we actually did an empirical check. Bruce Watson had a really good idea that didn't work. So they had olivine with a carbonate-rich melt, a carbonatite, and then they did those experiments, and then they dissolved out the carbonate-rich melt because it's very soluble in weak acid, and then they tried blowing air through that sample and seeing what the permeability was in that geometry. But for reasons I don't really remember, that didn't work. Okay, so the nice thing about this is that then we can simultaneously solve this steady state approximation and Darcy's law, given this permeability law, and we can solve for the porosity as a function of the upwelling velocity of the melt fraction and grain size, for example. And so you can make this sort of composite diagram where we're looking at height in the decompressing mantle underneath a mid-ocean ridge. And for example, we can say that the porosity for a fast-spreading ridge might get up to 2 or 3% at the top, and at a slow-spreading ridge, a smaller value, because basically the draining rate is pretty high. And we can look at the melt velocities, and you can see that at a fast-spreading ridge, the melt velocities might approach in a unchanneled system might approach a meter per whatever this is, meter per year, and the dashed one's about 5 times slower. There is a complication that if I get to the end of this lecture we'll come back to, and that is that the calculated permeabilities that I was discussing are based on an olivine-only matrix. And the idea is that olivine is wetting to silicate melt with a wetting angle around 30 degrees C. And that's basically why we see this interconnected and rather symmetrical looking triple green boundary network. Pyroxenes seemingly are not wetting to silicate melt. And so when Lujou and Greg Kurth went and looked at what happens if you have olivine-olivine pyroxene boundaries, pyroxene-pyroxene olivine boundaries, and unwetted pyroxene-pyroxene boundaries. Okay, and they distributed these combinations stochastically on a grid as a function of the olivine to pyroxene ratio. Okay, so for olivine-rich rocks, 80% olivine, 20% pyroxene compares very favorably to the von Bargen and Waff model, the numerical model that I showed you and that we tested empirically. Looks about the same. But as you increase the pyroxene fraction, so when there's only, for example, 40% olivine and 60% pyroxene, then the permeability diverges very dramatically from the von Bargen and Waff model, and you actually have a percolation threshold type permeability situation. So for pyroxene-rich periddotites and for peroxenites, they might be much less permeable, and in principle, pure peroxenites might be completely impermeable to melt flow in the mantle.
So, but the FOUL model assumed homogeneity, right?
He just said wetted green faces, yeah. But, so this goes back a ways. Toramaru and Fuji wrote the first paper on this in 1980, as far as I know, in 1986. And it's been an experimental observation. A lot of times when you do experiments on partial melting of mixed phase periddotites, the pyroxene grain boundaries aren't wetted. So there's a lot of empirical support behind this kind of approach. Okay, so the magical thing about mid-ocean ridges that determines the composition of the oceanic crust is that in this sweep of silica contents that melts in equilibrium with the mantle at different pressures, the mid-ocean ridge basalts sample this relatively low silica, 49% silica type composition dominantly, particularly at the East Pacific rise. So we see this very homogeneous stuff coming out, and it seems to record an average pressure of melting that's somewhere in the neighborhood of 1.5 GPa. Right? If this weren't true, if the melt continued to equilibrate with the mantle right up to the base of oceanic crust, then the oceanic crust would have the composition of andesite. It wouldn't be very different in composition from the continental crust, and plate tectonics would look a lot different. The whole surface of the Earth would look a lot different. So this magical ability of these rising melts beneath the spreading ridges to bypass the upper 45 kilometers of reaction with peridotite is a very important part of the melt transport process beneath mid-ocean ridges. I only think I left one triangular diagram in this talk after coaching from mineral physicists, but so this is the one and only one. But this is what that same kind of geometry looks like on a phase diagram with real liquid composition. So we filtered for magnesium to magnesium plus iron ratio greater than 66%. So things that haven't undergone a lot of crystallization and chemical differentiation in the crust. And we've plotted on these phase diagrams where we're looking at the proportions of olivine, clinopyroxene, and silica in these melts. And we've plotted the compositions of melts in equilibrium with the mantle at 25 kilobars or 2.5 GPa, 2 GPa, 1.5, 1 GPa. And you see that on both of these projections, the melt compositions of these mid-ocean ridge basalts that are coming out of the mantle cluster near the equilibrium phase boundaries for one, or they probably crystallize a little bit of olivine, 1.5 gigapascals. Okay, on both diagrams. So they've somehow magically bypassed the upper 45 kilometers of the upper mantle. And they can't do that by force flow. So these are dissolution rate data. summarized many years ago by Burley and Scarf in log centimeters per second linear dissolution rates, crystal dissolving inwards towards the center. And we're looking at, I've highlighted dissolution rates of the mineral orthopyroxene, and a range of temperatures from 1500 degrees on the left to 1250 degrees on the right that are appropriate for upwelling mantle beneath mid-ocean ridges and other places too. And you see that the velocities are in excess of 10 centimeters per year. So the crystal size isn't even 1 centimeter per year, it might be 1 centimeter. The crystal size might be 1 centimeter, and the rates of dissolution are very much larger than the diameters of the crystals. So there's really no way that porous flow could bypass the orthopyroxene crystals in the mantle and allow the melt to diverge from equilibrium with pyroxenes. So it would be andesitic if it all rose by porous flow through an orthopyroxene-bearing peridotite. We can also, I don't want to dwell on this too much, but we can also measure trace elements in residual mantle peridotites. These are rare earth elements from cerium to ytterbium on this diagram, normalized to chondritic abundances. We can measure pyroxenes in residual mantle peridotites that have been tectonically placed on the seafloor. We know how these elements partition between pyroxenes in these rocks and melts that they were in equilibrium with, and we can calculate with these hatch patterns the melts in equilibrium with the residual mantle peridotites that we observe on the seafloor, and we can compare those to the lavas that are sampled right next door on the same bit of seafloor, and we see this big difference in the incompatible trace element abundances, in this case between the light rare earth element abundances in these calculated liquids and the lavas that are observed. So this is another indication that the melts that come out at the mid-ocean ridges are not equilibrated with the shallow mantle residues from which they were extracted. And we understand this pretty well. You can understand these relationships as the result of something approaching Rayleigh fractionation, where you take out little bits of melt incrementally, and these lavas represent mixtures of melts that are removed over the whole decompression melting column, whereas these residues represent the most depleted residue of the very last little bit of melting. So understand it reasonably well, but for the purposes of this talk, it's also a good indicator of this disequilibrium between the mixed liquids and the shallow residues. So how to do that, all right? And so you can obviously do it in a couple of ways. You can have very rapid transport in a narrow conduit so that your diffusion distance is short but time is short. Or you can have slow transport, let's say porous flow, in a very wide conduit. So if we could make a crack and the melt went 100 meters per year or faster through this crack, then maybe it could preserve disequilibrium with the rocks around it. And conversely, if we're going to have porous flow, then the body that's carrying that flow has to be 1 meter wide or maybe even 5 meters wide in order to preserve disequilibrium between the melt and the matrix, because it has more time to talk. Going to observations, this is kind of a synoptic cross-section for places on the Earth where we see the lowermost oceanic crust and the uppermost mantle exposed on the surface. There are places where oceanic crust is thrust onto the continental margins, and tilted and eroded. And in particular in Oman, we can walk through these down canyons of these tilted sections and walk down 20 kilometers into the interior of the Earth. So that's a nice place to go. And so people have reconstructed this kind of cross-section. Here's the base of the oceanic crust. Olivine, clinopyroxene plagioclase rocks, gabbros, very strong seismic discontinuity between these plagioclase-bearing lithologies and the upper mantle. It's known as the moho. And you see there's foliation, so there's a planar structure in the mantle peridotites that's indicated by these light gray or light black lines. And then that foliation is transected by all kinds of melt transport features. There's these red blobs, which are olivine-only rocks, stonites. There are pyroxenite and gabbro dikes that are shown here, cutting the fabric at a very steep angle. So definitely cracks that filled with crystallization products of melt moving through the cracks. And then there are these kind of hybrid features where you see dikes surrounded by olivine reaction zones, dunite reaction zones. Okay, but you can look a little harder at this figure and see that if the foliation, if the planar fabric in the peridotite records upwelling beneath the mid-ocean ridge and then corner flow, then all these dike-like features cut that foliation at a steep angle, and they had to form off axis, away from the spreading ridge. So they're not really relevant to melt transport that feeds the formation of the crust at the ridge.
And none of those are dunites, the narrow ones, the cross cut.
None of them. We can go to Trinity and I'll be wrong, but in Oman, that's true. More to say, the melt that filled these cracks was saturated in the mineral orthopyroxene at low pressure. These are Websterites and Gabronorites, for those of you who care about such things. And so the melt that filled these cracks was not in equilibrium with the melt that formed the crust. In fact, it was very far from equilibrium with the melt that formed the crust. There's a whole bunch of reasons why we know that these crack-like dike features are not the way in which the melt was transported to the ridge to form the crust. And instead, these red things, these olivine-only dunites, are transposed along with the peridotite in which they're found, and so they have the structural features of things that form beneath the spreading ridge in the upwelling mantle column and could have fed the spreading ridge. Some of them get quite big. Here's these dun-colored rocks here are big wide dunites, olivine, a little bit of chrome spinel, and the brown rocks around them are residual mantle peridotites. They don't have a lot of clinopyroxene in them, so we call them Hertzbergites. And here's a castle for scale. So you can see that these dunites are the big ones are on the order of 20, 30 meters thick, and in fact the thickest one we know of is not too far away from this castle, is about 100 meters thick. So when we go to Oman, fortunately we find things that are pretty good analogy for what we dredge and drill from the mid-ocean ridges. And so for example, here the rare earth elements again, when added, lanthanum, normalized to chondritic concentrations. We can measure little bits and scraps of clinopyroxene that we find in the residual mantle peridotites. And they're very strongly depleted in these light rare earth elements, just like the abyssal peridotites that comprise this gray field that are dredged from the ridges. Okay? And if we calculate liquids in equilibrium with these, we get these kind of compositions. And if we look at the lavas that form the crust, we get these kind of compositions, and they're different by factor of 20 or so. So we can say that the lavas that form the crust in Oman were not in equilibrium with the shallow mantle residue from which they were extracted, just like mid-ocean ridge basalts. Whereas, when we look at little bits of clinopyroxene in the dunites, we see something quite different. Here's analyses of a bunch of clinopyroxenes in 4 samples. And we then went ahead and published this. So you can calculate liquids in equilibrium with these clinopyroxenes. They look like the lavas that form the crust in Oman, and they look like mid-ocean ridge basalts in this kind of diagram, with the caveat that there's 3 orders of magnitude concentration on this axis. Okay, so the dunites are the conduits for the kind of melts that form the crust, and they're also saturated only in olivine. They don't have any orthopyroxene in them. And so they not only can they preserve, or did preserve, trace element disequilibrium between the melts that went through them and the mantle around them, but they also preserved major element disequilibrium between these olivine saturated melts in the cores of the dunites and the pyroxene bearing rocks around them.
Peter, can I just ask, what is the CPX doing in those dunites?
No, really shouldn't be there. So it's the last bit of melt, presumably, that cooled and crystallized. But you're right, that's a good question. So there's a story here. I was gathering these data, and a pretty striking difference between the Hartsbergites and the host dunites, but I've done 10 samples of Hartsbergite, and I've only done 4 samples of dunite. And Bob Coleman, who some of you know is the dean of ophiolite geology, came in the lab and I showed him these data, and he said, "Stop gathering data now." And I said, okay, and so here's the paper. But I always felt a little worried that if we'd analyzed more than 4 samples, what would have happened? And so I'm happy to tell you that if we'd analyzed, these 15 samples, it would have come out the same way. All right, so the thing is about Dunites is that although they are oftentimes deformed along with their host peridiotites, they aren't always, and they locally cross-cut the foliation or planar fabric in the periodicite. And here's a case where there's a pyroxene-rich band in the host periodicite that's been cut by this dunite, and the pyroxene-rich band has a bunch of chrome aluminum oxide spinel minerals in it. And you can see this little trail of chromium spinel where the pyroxene-rich band used to be. Okay, so that shows you that the dunite is in fact not in a crack. It's not igneous new minerals filling a crack. It's a olivine-rich rock that's replaced these pyroxene-bearing rocks, and the pyroxene's dissolved away, and only olivine and spinel are left. You can't really tell if that was a constant volume process. It would be pretty hard to see a 10% volume change on this kind of geometry, but you can see that the dunites replaced their host rocks. Here's an actual photograph of that kind of texture. So here's a pyroxene-rich band, this is peridotite. This is a dunite, pretty sharp boundaries, it's typical on the grain scale. And you can see this little trail of spinels leading out from where that pyroxene-rich band used to be. This is my very first replacive dunite up in the Cascades. And you can see they have this typical anastomosing structure with these lenticular islands of pyroxene-bearing wall rock left behind in between these different tabular dunite bodies. And here's a map from the polar Urals that's much more beautiful than mine. You can see a lot of different features in this. You can see that there are blocks of relict peridotite left out in this big sea of spotted dunite, but they're not rotated with respect to the wall rocks. You can see in places that the dunites have preferentially replaced pyroxene-rich bands in the peridotite. What else? You can see that where the dunites cross material lines at an angle, there's no dilation or contraction that you can really measure. And so here's a little summary diagram. So we see no displacement of planar features across dunites. So if they were dilational and filled with minerals, they would look like that. We see these relic spinels sometimes, which really shows, without a doubt, that the dunite is replacing the rock that it's in. We see preferential replacement of pyroxene-rich bands. We see big dilational or big circular features in the dunites that are not accompanied by deformation in the surrounding rocks. We see this anastomosing texture that I already referred to, where the pieces don't fit together anymore unless the dunite used to be the well rock, and also they're not rotated. And then we also see, John, dikes with, or something that looks like dikes, with dunite reaction margins around them, and we even see interacting crack tips with dunite reaction zones around dikes. So there's no doubt in my mind that sometimes these dunites form as reaction zones around cracks. But all these textures, some of these textures make it hard to imagine there ever was a crack. And certainly all these textures, my attitude is no crack until proven otherwise. That said, for the sake of honesty, we have to show this figure. I like this because it looks like Henry Dick. I know Henry. I even have a little animated movie where Henry's head appears and disappears inside this red blob.
What's the front end?
What's that?
What's the front end?
I don't know, flames. So, and all this is here to say to us, first, a beautiful diagram, but that he was imagining these are reaction zones around cracks filled with melt, and it's left behind kind of a perfect crime, where there's this replacive carapace around this place where the blob went through. So that has to be said to keep everything honest. We can't really prove that they didn't open up and a whole bunch of melt went through and formed this big reaction zone and then they closed without a trace. After all, adiabatically rising melt in a crack in the mantle is undersaturated in everything. All it will do is dissolve wall rock. So what are you expecting to see? So then we moved into a sort of theoretical domain, which causes some discomfort. But there's some physics that pretty much originated from Dan McKenzie, where the overpressure between melt and matrix in a two-phase viscous interpenetrating matrix where the buoyant melt is rising through the dense residue is equal to the difference in density between the melt and the fluid. The maximum pressure difference that can be attained is equal to the density difference between the fluid and the rock, G, the gravitational constant, and this thing called the compaction length, which is related in some vague way that we can argue about for hours, to the permeability, the solid viscosity, and melt viscosity. And this might be as much as 10 kilometers. What did I want to say about this? The reason why there's a limit is that as pressure starts to rise, suppose we have an interconnected melt column sitting in a mass of hot mantle peridotite. If that melt column starts to generate an overpressure, the peridotite can just move out of the way. It's like pushing your thumb into peanut butter. It's very hard to generate a big stress at the tip of your thumb because the peanut butter just moves out of the way. And that's the sort of concept that's embodied here. So anyway, the biggest overpressure we can imagine might be on the order of 50 MPa. And people can argue until they're blue in the face whether 50 MPa is enough. It's not something that's been experimentally accessible. There's enough overpressure in the pores to cause the rock to break. It's not really tension, it's not really compression, it's overpressure in the pores.
So Peter, when you make that statement, how much porosity do we have to, are we at 1% porosity?
Porosity is not in this equation.
Actually, it's
All right.
But you opened the gate, you said porosity in the pores, and the pore fraction is exceedingly small.
Yeah, I mean, I wish somebody could do this experiment. But let's finesse it for now, okay?
Yep.
So the saving grace here is that, so if we imagined a porosity structure like this, where you have buoyant melt rising through a funny mantle where the porosity goes from 1% to 0.5% at a shock. The pressure, we've multiplied the excess pressure here by 10 so you can see it. So here's the magmastat, or actually the hydrostat, the solid pressure, and then this little excess melt pressure here forming around that obstruction in the flux. And here we've blown it up, and that pointy thing is 50 MPa, and it decays around that obstruction over a distance that's related to the compaction. So it's not very much, and it's pretty highly localized. So if instead we take that one-dimensional equation for melt flux beneath the spreading ridge, and we look at how the porosity varies in the decompressing mantle beneath the ridge, what we see is that the porosity is increasing always upwards. So the permeability is always increasing upwards, so the system is very well drained. And we don't see any structure like that where we're going to create big melt overpressures. There's a whole bunch of physics here, not all of which has been done, I would say. You can ask how big of a permeability or a perturbation around that simple porosity structure do I need to make it start to look like this? Okay. So there's a little bit of work been done on this, but at least I don't think enough. So we can ask, will that initial black line decay over time or will it grow? And I think the consensus at the moment is that in order for that black line to grow and begin to look something like this, you have to have some very, very significant effect of melt on the rheology of the solid matrix. And that would probably kick in at a melt porosity of around 5%. Okay, so again, I've shown you these steady state solutions for porosity, and they don't get to that limit, particularly not down near the bottom of the melting column. And so for the moment, we're going to continue to say that if I can't see a crack, then there wasn't one.
When you draw a figure like that, it's more or less saying that you don't have any effect of the melt concentration on the viscosity because you don't have any strain localization there. You're not displacing.
Not in this picture.
No, not in this one.
That's a very, this is Lanza peridotite. You could tell me maybe what it was, the tectonic setting and what was flowing through the Lanza peridotite. So instead, we're going to try and imagine a static process that forms these replacive channels. And we're going to draw on literature about something called the reaction infiltration instability, which at least came to my attention through papers by Peter Ortoleva and Chatham and others. Stiefel and Lasaga is cut off here for some reason. What they were looking at is a solvent flowing through a partially soluble rock. So we have, for example, acid flowing through a carbonate cemented sandstone. And there's a solubility front, so this fluid is coming in undersaturated across a planar front into this soluble porous matrix. And when that happens, under some conditions, if there's a perturbation in the permeability or in the soluble phase concentration spatially or something like that, then that dissolves a little faster, and then that in turn has a higher permeability and entrains more fluid. And it's a runaway, and you get exponentially growing dissolution fingers in the direction of fluid transport. I deleted these, Dave. But anyway, we fooled around with, it's kind of an ant farm, so we made you could call it a Healy-Shaw cell, it would be more polite, but it had glass balls and salt in here, and we ran tap water through it. And you can watch these dissolution channels grow. Learn a little bit the wavelength of the channel spacing starts out very short and gets longer, and the channels get bigger, and there's winners and losers, and so on. But the thing that bothered me about the ant farm and about Chatham or Ortoleva and so on is in nature, in the mantle, how would this dissolution front arise? How do we get this completely undersaturated fluid all of a sudden magically appearing somewhere in a reactive rock? And so we did this as a lattice-Boltzmann model. And we had a fluid that was represented by elastic little billiard balls, and you could imagine that the billiard balls coming in the bottom of this box are blue. And then we had solid particles that you can imagine were red, that are just sitting there in the way. Okay, you've got these elastic billiard balls bouncing their way down through a pressure gradient. And there's some probability that when a blue ball hits a red square, it'll detach a red fluid particle. And we have a solubility gradient, so the probability of detaching a red fluid particle depends on the concentration of red fluid particles. And it goes up as you go up through the box. So this is mantle rising through the mantle. Magma rising through the mantle simulated with billiard balls. And we left out one solid square right here, somewhere. I think it was here. What you see is that over time, a dissolution channel propagates around that permeability flaw. And what's cool is it propagates downstream and upstream. And at this point in the model, there is actually a solubility front at this end where the fluid is very far from equilibrium with solid particles in the middle of the channel. Okay, so you can get, this is how these things might arise out of a continuum. There's also some nice things to see in here about how the fluid pathways develop. So you see this coalescence upstream from the channel, and you see divergence where the channel, the permeability at the head of the channel begins to go down. Okay, it's just Bernoulli, but it's a good idea to keep this in mind when we think about how the solid system evolves over time and what sort of coalescence networks might form and unform. I think I'll skip over this for now. Cool experiment, minimal relevance. Okay, so the notion is that what happens in the upwelling mantle beneath ridges is that these dissolution instabilities get started somehow of some perturbation in something, and then eventually this olivine saturated liquid dissolves all the orthopyroxene out of this central conduit, which becomes a dunite. And then up at the top, as this begins to encounter cooling magma and crystallization and drops in permeability up near the surface, then you might see divergent flow and things, crystal little kind of pyroxenes forming in the middle of dunites and stuff like that. And from a theoretical point of view, the wavelength of the dissolution instability is determined by a few things, but one of them is the melt velocity. And so we had this notion that, okay, so Once I get a channel network at the smallest scale, the melt velocity has gone up. And so the wavelength of the instability should rise, and so we'll have a larger generation, a larger one. When we drew this, we didn't really know whether this dimension should be space or time or what, but we just wanted to, I don't know, draw a picture. So, and of course, this has a very, if I say that the width of these channels is somehow proportional to the flux in the channels, then I get a nice power law, a stupid power law, but a power law distribution between the frequency and the flux, or the frequency and the width. So that's something we might be able to go out in the field and look for. But first, Mark Spiegelman worked with us for many years, and we tried to do a very simple model of this dissolution instability, incorporating viscous compaction, incorporating this two-phase flow idealization where the buoyant melt is, the upward flow of the buoyant melt is coupled to downward flow of the dense residue. Okay, with the question, will they, as these channels begin to form, will they be crushed by compaction, so to speak? What will happen? So we have a viscous porous matrix, which is partially soluble. We have a solvent coming in the bottom. In this first set of models, the solid didn't go anywhere, so it just corrodes and corrodes over time. And we have a gradient in the solubility of some solid phase, just like the lattice-Boltzmann model that I showed you before, and it's a linear gradient. And if we visualize the resulting porosity structure at some time in just the right way, we see this nice coalescing tree, which looks a lot like that diagram that we call Einat's castle that I showed you a couple slides back. So a nice binary coalescing tree. And in fact, there's some math that you can go and retrieve from this 2001 JGR paper, where this dashed line is a linear analysis that pretty well predicts the number of channels at any given height, and it's decreasing upwards. That's the coalescence in that network.
This is all with respect to the computer simulation.
These are entirely computer simulation results. No messy reality. And we did lots of simulations at different dam color numbers, which is related to the reaction rate on the fluid flow rate, and Peclet numbers, which is related to the diffusivity and the fluid flow rate. In reality, unfortunately, reality lies somewhere off on the next floor and diagonally over in that direction. I don't know about the Peclet number, but certainly the dam color numbers are likely to be much larger than this. And no one, as far as I know, has done this any better 10, 15 years later. So one thing I want to bring out here is there's a parameter space here that really has never been fully accessed. And so what you can see is that, for example, there's kind of it turns out that dam color times Peclet is a pretty good predictor of everything. And so everything kind of evolves diagonally from the lower left to the upper right. But you can see that the wavelength of the channels goes down a lot as you go up in this direction. And so again, I'm not sure that we've got models that appropriately reproduce natural conditions in that, for example, in the wavelength. Being idealistic and living in the age of the fractal, we made wild extrapolations. And one thing that we were excited about was to show that, so we can see right in the field that little tiny Dunites go into great big ones. So we can see in the field that you don't have this nice hierarchical network where only big ones join together. You have little tiny ones going into big ones and so on. And so we just showed, okay, so for example, in your lungs, there's a nice distributory network of coalescing channels. And even though there's this side branching where very little channels access the very biggest ones, it still has a nice power law relationship between size and frequency and flux. And so like anyone would, we went out and bought a blimp. And this is known as the blimp for on-land oceanography, BOLO. And we had a little camera here and some fins, which we took off after a day. And actually, we bought this blimp from Adver Blimp in Sioux Falls, South Dakota. So you can get the blimp. Not too much. No, you wouldn't. You're right. We would use a drone. I mean, it's nice maps of these outcrops where the black stuff is Dunites and the gray stuff is Hartsburgites. And then we were able to do size frequency statistics on these maps. And we got kind of a poor person's power law here, 1 order of magnitude, not too impressive. There's also some mistakes here, but never mind. And then because Greg Kurth was a co-author and Greg never fails to extrapolate, we took this tiny data set and he said, well, what about Oman? What if we could really look at some big scales? Let's draw this line. And sure enough, okay, it seems to basically go through the map distribution of the very biggest ones on the geologic map. Enabled by this bold conjecture, we went out, we spent a lot of time making maps of these dunites in the host peridotite at lots of different scales. Here's one I like to take people to on field trips. Here's me, here's Greg. Mike Braun was back there in the projector taking these pictures, and then we have air photos, and we can zoom out in that area, and that previous image is here, and this is the biggest one there is. 100 meters, here's the coastline, here's the Sultan's Palace blacked out by the sensors. And so out of these data, actually it turns out, here's all the photo interpretation, looks like earthquake data, kind of ugly. The best data set is hands and knees with a tape measure of about a week. And so we get this nice frequency width relationship that persists over about 4 orders of magnitude and 5 orders of magnitude. And furthermore, you can look at that network and you can say, okay, let's assert that the frequency of a given width is proportional to the flux. And we'll imagine that the frequency is proportional to the melt velocity, to the fractal dimension +1, and therefore the flux is related to the width, to the velocities. And when we do that, we can show that there's plenty of melt that can flow through the dunite conduit network alone. We don't need any cracks. Porous flow, very slow porous flow, can satisfy the flux constraints that we know from the rate at which oceanic crust is created above spreading ridges. So there might be cracks, but we don't need them. Okay, and then bold extrapolation takes this and makes that. Everyone should keep in mind that this is a cartoon. It's not based on the model. It's not even really based on the observations. It's just a picture of how things might be. I started out with a tree because it looked like a mandala, and I was excited about that. And I realized it has to be a bush. It's just a cartoon. But anyway, maybe these observations in this kind of scale plus the models can inform something that looks like this. Coalescing network of dissolution channels that forms at about 45 kilometers depth and carries melt through it, avoiding equilibrium with the surrounding peridotite, which is still undergoing partial melting, and feeding these channels as it goes up, but allowing the crust to preserve some average pressure of equilibration with the mantle that's down here. And now maybe I will talk about this picture. I wonder if I can make this movie. There are a lot of other things that I think this kind of dissolution instability might be relevant to, that I haven't really seen well developed yet. And one of them, of course, is hydrothermal chimneys on the seafloor. What most people will tell you in the ore deposit business or the hydrothermal alteration business is that chimneys form at the intersection between two faults. And that's probably true. But that's a terrible way to find an ore deposit because there are millions and billions of intersections between faults. And only some of them have an ore deposit on them. So we need something more to understand the spatial localization of individual chimneys and ore deposits, for example, along the mid-ocean ridge system. And you can do these nice experiments, for example, where this is ammonium chloride in a tank cooled from below. Some of you might be familiar with Steve Tate and Claudia Parr's work on this system. This is our particular realization. It's cooled from below. The solubility of ammonium chloride in water is very strongly temperature dependent. Return flow of dense ammonium chloride rich water comes down, it cools, it crystallizes ammonium chloride. That in turn makes it less dense chemically as it rises back through the tank because thermal diffusion is faster than chemical diffusion. You have relatively fresh water that's heating up, and you make these nice dissolution channels, little volcanoes in the bottom of the tank. So something like this, I think, would be pretty easy to understand, incorporating, for example, the temperature dependence of solubility of anhydride. I'm going to get through part of this stuff, but that's okay. So there's this nice paper. So the oil companies were interested in the dissolution instability, which they called acid flooding, with the idea of using it for enhanced oil recovery. And so there's quite a bit of work done in the late 80s and early 90s, and this is this nice paper by Hofner and Fogler in, what is this, American something, Chemical Engineering. They looked at a bunch of different, they did acid flooding of plaster or limestone and got cool looking things that they cast with woods metal. I've done this, it's possible for all of us to do this. And then they also had a network model, and I'm just showing you the network model here. And they say that these are going in order of decreasing damped color number, which sounds very fancy, but really what they're doing is varying the pressure gradient that's driving flow through this model and that leaving everything else constant. Okay, so really slow flow velocities. There are perturbations in the porosity and permeability here, but they don't grow into channels because chemical diffusion across the fingers is enough to homogenize the soluble phase concentration. So there's no advantage to being in the finger. At intermediate flow rates, the fluid in the fingers remains strongly undersaturated, and you get these dissolution channels that eventually break through the system. And then they get very big and they startle all their neighbors, things that I already showed you take place. But if you increase the flow velocity still more, then the liquid doesn't equilibrate with the matrix anywhere. It's always a really strong solvent, whereas here, liquid going in the slow path out here is saturated in the soluble phase. But here it isn't. And so every single grain boundary or every single pore turns into a channel, in which case there's no channel. And so what I think is kind of interesting about this is it kind of closely mimics what we might think about rain falling on a sandy surface. Okay, so very, very small fluxes, the rain goes into subsurface pore space, and there's no channeling of any kind. At intermediate rates, you get nice sapping channels and erosional channels on the surface, and at very, very high rates, you get sheet flow down the surface 2 dimensions, so you don't really have any structure. So if in my dreams, there was going to be a thermodynamics of erosion, both chemical erosion and plastic erosion, that exploited the similarities between the dissolution instability that I showed you and a depositional instability that I'm not going to have time to show you unless you stick around. But what I'll call to your attention is that in this sapping channel network on a beach, there's this nice coalescing network of channels, but the other thing is that they're all active at the same time. So each little guy is feeding the big trunk. In this depositional system, it looks symmetrical to first order because the flow is diverging, as in the schematic pictures that I showed you earlier. But there's a big difference, and that is that at any given time, only 1 or 2 channels in the delta are. Okay? And if I had time to show you, I'd show you experiments where we can simulate this for reactive porous flow with a crystallizing fluid in pore space. Buildup of armored channels because the fast path crystallizes the least. Then they clog up, and the fluid seeks another path and another path, and ultimately it fills space. But at any given time, only 1 conduit or maybe 2 are active. So I think there's a real non-trivial relationship between the geometries of this kind of erosion and the geometries of the chemical erosion that I've been showing you. But I'm not smart enough, it turns out, to really develop that, so I'm telling you about it instead. Let's see some things that are really wrong about this, and then I'll end there. So we've made a big hoo-ha about how the dissolution channel instability explains melt extraction beneath mid-ocean ridges, but you don't see anything like this structure in this diagram, and in particular, there's no side branching in this diagram. So what we see in the field is a huge range of sizes at one depth, the top. But in this diagram, we only see one size at any given depth, pretty much. And the porosities are very high in these channels at the top and very small in these channels at the bottom, but we don't see a lot of side branching. We're not predicting it. And it's not just a function of the color map in the way that I've scaled these data. So we don't really understand how the outcrop scale features, the smaller outcrop scale features that we're seeing form. And I would say we don't understand the physics in this region, the interchannel region, very well at all. I don't know if this is a resolution problem or something problematic about the physics. You could imagine on very small scales, it's more like the dissolution instability in a rigid material than it is like the dissolution instability in a two-phase interpenetrating viscous network. So that might be part of it too. But if the models are good and the compaction lengths are right, we should be able to account for that, but we're not. Or we just don't understand what we're seeing.
Peter, can I just ask real quick, is it a possibility that, going back to Henry's diagram, that when you look at the outcrop scale now, or in the field now, you're seeing this, at one depth, you're seeing a distribution of different sizes. Do they all have to be channels contemporaneously?
No. So some of those dynes could be residual porous dissolution channels that were active lower down, and some could be recent.
What's the porosity?
But even when we do soluble phase maps, we don't see nice side ranging. Right? We can map the distribution of soluble phase after some history. Instead, we tend to see these big channels with big wavelengths at the top.
What's the porosity like in the thicker channels?
I could show you that. I
Alright.
have that slide here, right? Trying to reduce the number of slides I was going to show, I threw it down to the bottom. Stick around. It's time to evolve now. Okay. Another thing that's making its way into the discussion, I can vaguely hear this murmuring while I'm working on weathering, is that the depth at which the dissolution instability arises in the specific geometry underneath the mid-ocean ridge may not be something that we can understand through the reactive infiltration instability. So let me see if I can explain that really quickly. This model, for example, had a static solid that's partially solid. So we can run fluid, we can run solvent through that forever, and obviously eventually something will happen. But beneath the mid-ocean ridge, the stuff starts melting down here, and it goes off stage left and right up here, and it only has a finite lifetime in the reactive column. And so is there enough melt reacting with little enough peridotite to really make these channels in the time that's available? And again, I don't think this parameter space has been examined very well. So you'll have Dan, certainly McKenzie, and Rich Katz saying maybe not, don't know. But we found early on that the onset of channels was related to some very tweaky little parameters that we didn't even really mean to be modeling. Things we put in to keep the model from crashing at zero porosity and stuff like that. And so I gather there's still some uncertainty about the rheology of peridotite as a function of the melt fraction at very low melt fractions. And so this should probably be re-examined just looking at that parameter space and trying to figure out. But the alternative, of course, is that the channels get started from some bigger perturbation. I just want to emphasize some of those things that we do see. So this rubbly stuff, it's not a great reproduction from a 1995 paper, but this rubbly stuff out here is mantle peridotite, and this really rubbly darker stuff is a pyroxene-rich band. Same over here. And what you can see is this little dunite has preferentially replaced the pyroxene-rich band. So where the soluble phase concentration is really high, like bands of recycled oceanic crust in the convecting mantle or whatever your favorite thing is, eclogite, whatever, those will be pathways for preferential dissolution, and then they can kick off larger instabilities as they become conduits of focused flow. And similarly, we do observe natural examples where dunites, in this case are black, are focused along deformation features like this shear zone here, where this length scale is about 50 meters. Okay, so we know that in some places, perhaps, let's say, incipient dilation associated with shear deformation can interact with feedback involving melt transport that may lower the viscosity, runaway. But so deformation features may be the thing that gets the localization started, and the channels as chemical entities might be more of a consequence than a cause. And in that context, just mentioned results that are probably coming out from Rich Katz and probably Dave Kolsted's lab and so on, where if you think that shear localization is important, that's kind of convenient because I've drawn this picture badly, but the corner flow should follow about a 45-degree angle for a lot of solid upwelling geometries, and that's about what we need for the coalescing angle for the coalescence angle for channels. So that might be fortuitous, or that might be the right answer. So I've been talking, I mean, we had trouble with the projector, but I still feel like I've been going on for something like 50 minutes. And I have like 50 more slides, but I don't think I'll show them. And so, subject to what you want to talk about, I'll end here. Thanks.
Thank you very much, Peter. Questions?
Maybe a stupid question, but how long can a dissolution channel survive? I mean, when you form it, does it stay? Is it a static thing?
Yeah, right. So
Or can they reform or combine or?
Reform or combine, I don't know. But the very first ASU talk on this I ever gave, this imposing fellow named Dave Stevenson was on his feet before I even finished. And his point was that compaction was going to close these things down. Because his notion was that when they are porous, they are weak, and when they are weak, they should compact very rapidly. What we found actually when we modeled that was that it's kind of the other way around, that the interchannel regions tend to compact down pretty tight, and as long as they still have some food, the dissolution channels keep growing. So that's the answer to one question. But in this geometry, obviously there is a place where this conduit no longer has the right orientation to take melt flow to the ridge. In fact, ultimately it's pointing the wrong way. And so presumably they die, and I've sort of symbolized this by they're getting deformed and dismembered off here, but it's just to make it accord with what we see. Right? There's no physics there. But watch this spot, because Mark Spiegelman and coworkers did some corner flow model with channels, and now there's a real factory for that in Oxford, and so Rich Katz and Toby Keller and people like that are doing really pretty sophisticated, possibly over-parameterized, but very sophisticated models that involve corner flow. And I've seen some nice pictures that look like that, which is very gratifying, but doesn't mean they're right.
So what happens to the channels when they've been rotated? Are they stretched or flattened? Or
well, what we see is that a lot of them are locally discordant to the planar fabric in the peridotite, but they're elongated in the right directions. And then they have olivine deformation fabrics that are pretty much parallel to the olivine fabrics in the host rocks, but are stronger. And the reason why those fabrics are stronger is a matter of conjecture. It could be because there's more strain in the dikes, or it could be just grain growth, because there's no pinning phase.
Andrea?
How much melt production you need so that you never get oversaturated back in silica when you are going through a pyroxenite?
So it's about the solubility of orthopyroxene in melt. If you just want a quick envelope number, it's about 1% per kilobar of decompression. And so if you have a rock that's 100% melt, 100% pyroxene, then you're going to need, and your melt is decompressed by 10 kilobars, are you following me? Then you're going to need a melt rock ratio of 10.
So you need a lot of production.
Yeah. For Hartsburgite, you need a melt rock ratio of around 2. And it's interesting to think about, this is something when you're hiking along in Oman, you try and do in your head. What if there weren't any channels? But we know the flux because we know how much crust is formed. There'd be little or no pyroxene left in the uppermost mantle beneath spreading ridges, and the crust would be andesitic. Yeah.
What happens in the third dimension? Are these
Yeah,
channels
that's a good
or planar features?
Well, as I showed you,
Both
they
theoretically
are
and in the field.
They are in the field. I guess you can tell from this picture, planar. Right? So they're extending into the outcrop. This surface is roughly perpendicular to tabular features. Lenticular and so on, but they have a planar aspect. Whereas, if we run dissolution models in 3D in a rigid material, for example, then we get nice cylinders, sort of Hieronymus Bosch anatomical things with people crawling in and out of them. So why is that? And there's a couple of easy answers, and then there's the terrifying prospect that everything I said is wrong and they're actually light diffractions. But so there could be anisotropy in the permeability in the rocks to begin with, and it doesn't take much. There could be anisotropy in the stress. There could be anisotropy in the strain. So there's a whole bunch of things in a two-dimensional corner flow geometry that might be inclined to give you planar rather than cylindrical features. But again, this hasn't been very well tested in any numerical model. There's something out there. No, Mark didn't publish it. So Spiegelman has given talks where he was able to produce planar geometries with anisotropic permeability, but they're just AGU abstracts. Herbert, you had a hesitant, incipient hand.
Do you have any further questions?
If you want to stick around, I'll talk about crystallization enforcement. We'll flip the polarity.
What I should say is, if you want to carry on discussions, we should lubricate them with some beer. We're going to go to the pub. We're going to go to the Castle pub, so everyone's welcome to join us. Peter will also be giving another talk tomorrow downtown at 4 p.m. I can't remember the title.
I don't remember the title, but it's something about converting art crust to continental crust.
Yeah.
Volcanic art crust to continental.
You haven't prepared the talk yet.
I have. I've given it many times, but I don't remember.
Could we thank Peter?
I'm not normally proud. It's in Nature's Geoscience. But we got the cover. We got the cover, and it's a climb that my wife and I did. Nature does